In section 1.7, we're going to introduce the idea of linear independence. This is actually a pretty big idea in linear algebra. It's one we're going to refer to pretty frequently throughout the rest of the quarter. And for such a big idea, you're going to find it's really an idea that we already know, just wrapped up in some new language. So let's take a look at what's going on here with the idea of linear independence. Let's just start with an example. So I'm starting with a system of linear equations, and we now basically have four different ways to write down the same system. We have all the way back to the just linear equations written out as equations. And then we can write that as an augmented matrix. Sometimes they put this little dashed line in here to indicate that it is augmented, that the equal sign's been included. Don't have to include that if it's clear from the context. You can also write this as a matrix equation. This is the one where you have let's get in the right color. This is where you have the form of AX equals B is usually what you call those. And then in the blue here, we also have what they call the vector equation. All four of these forms saying exactly the same thing. We are actually going to focus on this fourth version here, the blue, the vector equation. And since this is a homogeneous system, right, it's equal to 0, notice that I can rephrase this another way. I'm basically saying, can I somehow combine all three of these vectors to produce 0? If I maybe subtracted this whole x3 term, moved it over to the other side, I'm not actually going to write that out. But another way of saying this would be, is there some combination of the first two vectors that will produce the third vector? Or if I moved x2 over to the other side, it would be, is there some combination of x1 and x3 that will make x2? Or same thing with the first vector. And notice by leaving it equal to 0, 0, 0, it's just saying, is there some way to combine two of the vectors to produce the third? So maybe that's worth writing out. Is there some way to combine two of these vectors to produce the other one? If the answer to that is yes, then there's linear dependence. One of them depends on the other two. If the answer to that question is no, then we have linear independence. Let's say all three of these vectors are independent of each other. I can't just combine two of them to get the same effect as I would get from the third one. So let's introduce the formal definition. Actually, the formal definition is in the book. This is my slightly simplified version. A set of vectors is linearly independent if the vector equation x1 times v1 plus x2 times v2 and so on equals 0 has only the trivial solution. So keep in mind a homogeneous system always has the trivial solution, and definitely looking at any of these forms, if you put in 0 for x1 and 0 for x2 and 0 for x3, that will solve the equation. But that does not mean that you can somehow combine the first two vectors to get the third vector. So that's the trivial solution. If there's any other solution besides that, then we have linear dependence. If 0, 0, 0 is the only way to do it, then we have linear independence. So let's go ahead and see if we can figure out if these three vectors are linearly independent. So that's probably the way we're actually going to see this question asked in section 1.7. It would be something along the lines of, are these three vectors, that one, and this one, So they'll say, is this set of vectors, so are these three vectors linearly independent? We'll get some shortcuts that work sometimes, but in general, the basic method is just to try to solve this system. So go ahead and dump those into row reduced echelon form. I actually didn't include the zeros for some reason on the end of this, but you know when you row reduce, they would just stay a column of zeros. So look at the output here. If we are trying to solve this, we get something like, let's see if I can squeeze it in here. X1, and this would be minus 2x3 equals 0. Pretend there's a little zeros on the end here. But I'll move the equals 2x3 and x2 equals negative x3, and x3 is a free variable. So you get x3 equals x3. So you'd say any combination of 2, negative 1, 1. Or to put it slightly another way, the answer here is no. They're not linearly independent because 2 times 1, negative 2, 3, minus 3, 1, 2, plus 1, 5, negative 4 equals 0, 0, 0. And let's just check to make sure that's actually right. So let's see, on the top we'd get 2 minus 3 is negative 1 plus 1 equals 0. The next row would get negative 4 minus 1 is negative 5 plus 5 is 0, and finally we'd get 6 minus 2 is 4 minus 4 is 0. So yeah, this is linearly dependent. If we really want to be explicit about the linear dependence, we should really show how you can combine two of the vectors to make another one. So if you really wanted to write a dependence relationship, I'm going a little bit beyond what we really need to do here, but to really be explicit, you could say 2 of the first vector minus 1 of the second vector would make negative 1 of the third vector. And I guess you could multiply both sides by negative 1 if you really wanted to fully make this clear. And just say, yeah, this is how you could combine two of the vectors to produce the third vector. So this is the basic idea so far of linear independence, is just to say, can you combine your vectors and produce the zero vector without using all zeros, without using the trivial solution? If that's true, then we don't really need all three of them. What we just figured out right here is that any time we might have needed 1, 5, negative 4, I could have just used negative 2 of the first one and 1 of the second one instead. Graphically, what that means, and I'm going to try to draw some three-dimensional vectors here, which isn't going to work, but basically what that means is, let's get on the right layer, and let's get off the eraser. Okay, here we go. Basically what that means is if you have your three vectors, one of them points off this way, and one of them points off that way, and another one points that way. I don't know, I'm just making that up. There's no relation to the actual vectors. But the basic idea is if you want to get somewhere in space, like here, and you think you need 1, 5, negative 4 to get there, you don't. You can combine the other two in a certain way to get there instead. In my little picture, it sort of looks like if I could take about one of this vector and maybe like 2.5 of that vector, I can get anywhere that third vector would have taken me. So I think my little picture here ended up being a drawing of linearly dependent vectors, right? Because the 3 vectors, wherever this third one gets, I can do it with the first 2, with that one, and then 2.5 of the third one. If this was an Etch-a-Sketch, it basically has 3 knobs, and we don't need 3 knobs to get where we're going. We only need 2. If I can twist those 2 knobs enough, I'll get to any point in the space that I could get with the third knob as well. Okay, so we'll look at a couple more examples in the next video.